need to separate ethanol from water? The key is their difference in volatility. In batch distillation, we heat the mixture. The vapor rises, starting the separation process. Initially, we use total reflux. All condensed vapor returns to the column to maximize efficiency. This crucial stage significantly boosts the ethanol concentration at the top, ensuring high purity. Once stable, we collect the high-purity distillate while maintaining optimal reflux for continuous quality.
Alright, the table shows successful separation in a batch distillation process where the top product maintains a consistently high reactive index from 1.3617 to 1.3651, indicating a high purity of the more volatile component, while the bottom product shows significantly lower values 1.3373 to 1.3509 due to the concentration of the less volatile component in the reboiler. The reason for these distinct values lies in vapor-liquid equilibrium, where the rising vapor becomes enriched with the more volatile component and condensed at the top, while the heavier residues remain at the bottom. The minor nonlinear fluctuations observed across the different reflux percentage 300 down to 30% occurs because this is a batch operation, meaning the composition of the boiling mixture in the pot continuously depletes over time, creating a dynamic interplay between the changing pot concentration and the varying reflux ratios. Alright, so for discussion, number one, discuss the advantage of a bubble cap distillation column compared to sieve plate and valve plate columns. So the answer is the comparison of three types highlights why the bubble cap tray is uniquely suited for the highly dynamic nature of batch distillation over sieve and valve plates. In terms of whipping, bubble caps offer zero risk because their physical risers extend above the liquid level to maintain a positive seal even if vapor flow completely stops, whereas sieve plates suffer from high whipping risk at low vapor velocities, and valve plates carry a moderate risk if their moving components wear out or stick. This structural geometry grants bubble caps an excellent turn-down ratio, giving them the operational flexibility to handle the continuously depleting vapor loads of a batch cycle efficiently. Compared to the poor, narrow operating range of sieve plates and the moderate flexibility of valve plates. Furthermore, while bubble caps represent high cost and complexity due to the heavier construction of caps and risers, sieve plates remain a cheap, low-maintenance option with simple drill holes, and valve plates represent a medium-cost compromise. Ultimately, because a batch reboiler's composition and volume constantly deplete over time, the bubble cap column's unique ability to guarantee a stable liquid level and eliminate whipping make it the ideal choice for sustaining high mass transfer efficiency from the beginning to the every end of an unpredictable batch cycle. Alright, so for question 2, as a process designer engineer given a set of product output quality and flow requirement, describe how you would proceed in designing the distillation system and calculate the cost of operations. Alright, so for the process of design workflow, we need to do a thermodynamic selection and flow characterization, where the initial step involves fully defining the physical and chemical properties of the raw feed stream, including its composition, temperature, pressure, and mass flow rate. The engineer selects an appropriate thermodynamic fluid package within a process simulator to accurately model the non-ideal vapor-liquid equilibrium behavior of the specific chemical components. Then we need to have the shortcut design calculation, where using analytical engineering equations, the engineer established a baseline for the column's performance. This involves calculating the minimum number of theoretical stages required at total reflux and determining the minimum reflux ratio necessary to achieve the target product purity and recovery constraints specified by the client. And lastly, rigorous simulations and optimization. The shortcut design parameters are imported into a rigorous fractionating model to fine-tune the system. The engineer runs multiple iterations to optimize the exact location of the fit tree, ensuring it matches the column's internal composition profile, which directly minimizes the overall energy required by the reboiler. And then for the evaluating operational costs, OPEX, we need to energy balance determination, where it's to evaluate the ongoing cost of running the system. The engineer extract the total energy requirements from the completed simulation. This focuses on compiling the thermal duties on the reboiler, the thermal duties of the condenser, and the electrical power consumption required to the run the reflux and feed pumps. And then we need to do the utility consumption mapping. The calculated energy duties are translated into the consumption rate of actual plant utilities. The reboiler duty detects the mass flow rate of heating steam or hot oil required. The condenser duty determines the volumetric flow rate of cooling water of refrigerant needed, and the pump duties define the kilowatt-hour electricity consumption. And lastly, economic optimization, CAPEX versus OPEX. The engineer performs an economic balance to find the most cost-effective operating point, usually targeting an operating reflux ratio between 1.2 and 1.5 times the minimum reflux ratio. Increasing the reflux ratio yields higher productivity and a shorter, cheaper column, lower capex, but drastically increased steam and cooling water consumption, higher OPEX. Require a careful life cycle cost analysis to find the minimum total cost. Alright, so for the conclusion, in this batch distillation experiment, an ethanol water mixture was successfully separated using a separate column. The arrangement of ethanol in the distillate and the accumulation of water in the reboiler were clearly indicated by the refracting index of the top product, which remained consistently higher than that of the bottom product. The separation efficiency was generally enhanced at higher reflux ratios because returning more condensed liquid to the column increased both vapor liquid contact and mass transfer efficiency, while minor fluctuations were observed in the refracting index reading likely due to temperature effects, sampling errors, and operational instabilities during the run. The overall results align closely with the theoretical principles of batch distillation and reflux operation. I think that's all from me. Thank you.